we are going to discuss how to express the concentration of different solutions. And what we are going to use is molarity. And it can be deathly important to know the amount of solute to put in a solvent to make a solution, right? If you want to kill some rats, you better make the solution concentrated enough. And the general idea is first you do your calculations, and then you mass out some solid. You put it in the right volumetric size flask, and I'll show you one of those. And you add some water, get it to dissolve, then you fill it up to some little mark to some final volume. And then we'll know what the concentration is. So molarity. What is the difference between a solute and a solvent? Well, the solute is what you're dumping into the flask, right? And the solvent is what you're filling it up to the mark with. Now, what's interesting is that a solute, the solute, does not need to be a solid. The solute could be a liquid. The solute could be a gas. The point is that there's always less solute than solvent. Whatever you have the most of in a solution, that's the solvent. So whatever you have the most of, that's the solvent. So you can have a whole bunch of things dissolved in water, but the point is that it's mostly water, so water would be the solvent. Also called an aqueous solution. When water is the solvent, it's called an aqueous solution. Molarity is used to describe the concentration of a solution. Molarity has units of big capital M. How do you read this? We're not supposed to say 0.21 m sodium chloride. We should say 0.21 molar sodium chloride. What equation is used to calculate molarity of a solution? Well, molarity is just moles of solute divided by liters of solution. So if you want to know the concentration of a particular solute, just divide the moles of that solute by the liters of the solution. How do you solve the above equation for liters of solution? The reason why I'm asking you that is I just want you to get used to doing this. Recognize what's on top and bottom, and you can always go along the diagonals. So in other words, liters of solution then would be the moles of the solute divided by big M, the molarity. So that's all I'm interested in showing you. Dilution. How can a solution be diluted? Simply you're adding more solvent. Whatever that solvent is, add more, and the concentration goes down. The solution is diluted. When solving dilution problems, what does not change during the dilution process? We're just adding solvent, not solute. So the moles of solute does not change. Right? What doesn't change? It's the moles of the solute. What equation is used for all dilution problems? MiVi equals MfVF. Okay, so Mi is the initial concentration, Vi, the initial volume, Mf, the final concentration, and Vf, the final volume. So we use this equation when we have some really concentrated solution. And you want to make a dilute solution. Okay? So MF is going to be that final concentration, that concentration of that dilute solution. VF would be the volume of that dilute solution. MI is the concentration of the really concentrated or the stock solution. And VI is the volume that you take of that stock solution. Let's see what a dilution problem looks like. You recently purchased online a very concentrated solution that contains an entire year's supply of blue vitamins in a single bottle. Now, every morning, you need to prepare 100 mils of 0.59 molar blue from the bottle of 11.7 molar blue concentrated vitamin water. How would you prepare your daily solution of vitamin water? First, this is a dilution problem. Look at this. They have two concentrations. Whenever you see a problem with two concentrations, this is going to be a dilution problem. So we could go ahead and write our equation down in the first place. MIVI equals MFVF. And when you see the words, how would you prepare, this is the statement that's the easiest and the most concise to make. Take VI of MI and dilute to VF to get MF. Okay, we just need to figure out what these variables are going to be. We don't know what VI is, but we know what MI is. What's the initial concentration? What's the stock solution, the most concentrated solution, the initial? It's 11.7 molar, right? It's that stock solution. It's concentrated. Dilute to VF. What's the final volume? The final volume is 100 milliliters. To get MF. MF is the final concentration. It's the diluted concentration. It's the smaller concentration. 0.59 molar. So that's our answer. Take VI of 11.7 molar and dilute to 100 milliliters to get 0.59 molar blue. We just have to figure out what VI is. Okay, let's calculate it. MI is 11.7. We'll solve for VI. MF, we said, was 0.59. VF is 100 milliliters. Notice the units that cancel out. Molarity cancels. VI is going to be in units of milliliters. We didn't even need to convert to liters, right? Just leave it in milliliters. It works. So take 0.59 times 100, 0.59 times 100 divided by 11.7. What's VI? 0.59 times 100 divided by 11.7, I get 5 milliliters. So you erase the VI, 5 milliliters. That's our answer. What would it look like to actually make this dilute solution? Well, here's my MI, my concentrated 11.7 molar blue solution. This is a volumetric flask. I grabbed a 100 milliliter size because that's what our final volume should be. So when I fill this flask up to this mark, I'll have exactly 100 milliliters in this volumetric flask. This is a graduated cylinder. I'm going to use this to get the VI, or 5 milliliters, of my 11.7 molar blue. So first I'll get my 5 milliliters. There's my 5 milliliters of blue. Add it to my volumetric flask. Now all I do is just fill it up to the mark with water. There we go. It's filled up to the mark with water. Here's this solution is now 0.59 molar blue, and I have 100 mils of it. Take VI of MI, take VI of Mi and dilute to Vf to get Mf. Now this problem was a dilution problem, and I think it's easiest to recognize because we had two molarities in the problem. Take a look at this problem. Describe the steps to prepare 100 milliliters of aqueous solution of 0.55 molar sodium chloride from solid sodium chloride. There's only one molarity in this problem. This is definitely this type of problem. Molarity is moles over liters. In this case, moles of sodium chloride over liters of solution. Your answer is just going to look like this. Add this many grams of sodium chloride to 100 milliliters of water. Why 100 milliliters? Because, well, that's what they wanted. Okay, we just have to figure out the number of grams of sodium chloride. The answer is right here. Let's just solve for moles, then use molar mass to convert to grams. So my molarity is 0.855. My moles of sodium chloride all over liters of solution. I have 100 milliliters. 100 milliliters, you can just move the decimal place over 3 places or divide by 1,000. There's 1,000 milliliters in a liter. So that would be 0.1 liters. Right? Move the decimal place over 3 places. 1, 2, 3. 0.1 liters. So that goes in the bottom. So my moles of sodium chloride is going to be 0.855 times 0.1, which is 0.0855 moles of sodium chloride. Now, how do you convert that to grams? Use molar mass. 0.0855 moles of sodium chloride divided by the molar mass of sodium chloride. Sodium is about 23. Chlorine is about 35.45. So that's a total of about 58.45 grams of sodium chloride in a mole of sodium chloride. 0.0855 times 58.45, about 5 grams of sodium chloride. So there's my answer. Add 5 grams of sodium chloride to 100 milliliters of water. So how would I prepare this solution? I have my solid salt, my 100 milliliter volumetric flask, and some water. Put the weigh boat on the balance, tare it, and once it reads 0, I'll try to add exactly 5 grams of salt. That's pretty close. Add my salt to my volumetric flask. Add 100 milliliters of water. Maybe get it to dissolve first. Okay. And then fill it up to the mark. There we go. We have 100 milliliters of 0.855 molar sodium chloride prepared from salt and water. If 48 grams of sodium chloride is dissolved in 250 milliliters of water, what is the concentration of sodium chloride in the solution? So do you recognize what type of problem this is? This is not a dilution problem. This is another molarity problem. Okay? And they are after the concentration of the solution. They're after big M. So all we need to do is find moles and liters, divide the two, and we'll have our answer. We have 48 grams of sodium chloride. And remember, the molar mass of sodium chloride was 58.45 grams in a mole of sodium chloride from the periodic table. So 48 divided by 58.45, well, 0.821 moles of sodium chloride. So we'll have 0.821 moles all over 250 milliliters. And 250 milliliters, move the decimal place over 3 places. 1, 2, 3. 0.25 liters. Right? If you're not sure about moving the decimal place, just divide it by 1,000. So 0.821 divided by 0.25, I get about 3.28 molar. 3.28 molar sodium chloride. So if I add 48 grams of sodium chloride to 250 milliliters of water, my concentration will be 3.28 molar sodium chloride. How many milliliters of water should be added to 45 grams of sodium chloride to prepare a solution of 1.25 molar sodium chloride? So again, notice there's only one molarity in this problem. This is not a dilution problem. This is going to be a single molarity problem. Big M is moles of sodium chloride all over liters of solution. They want to know how many milliliters of water should be added. Well, we're just going to solve for the liters of solution. That's our answer. And then just convert to milliliters. The moles of sodium chloride is right here. We just have to convert. We have it. So let's try this. We'll have 45 grams of sodium chloride. Convert that into moles. We know that there's 58.45 grams in a mole of sodium chloride. .45 divided by 58.45, about 0.77. So my molarity, 1.25, has to equal 0.77 all over my liters of solution. Now you remember how to do this. We want liters of solution to the other side, so you just move along the diagonal. So pretty much liters of solution goes to the top, and that 1.25 goes to the bottom. So 0.77 divided by 1.25, you get about 0.61 liters. Move the decimal place, or if you're not sure about moving the decimal place, just multiply it by 1,000. That'd be 610 milliliters. You have a 250 milliliter solution of 1.5 molar ammonium chloride. How many mils of this solution would be required to prepare 500 mils of 0.25 molar ammonium chloride? Do you see what type of problem this is? You see the two molarities? This is definitely a dilution problem. So Mi Vi equals Mf Vf. The more concentrated ones are supposed to be the MIs, but it really doesn't matter. You get the same answer no matter what here. But let's just be consistent. I's, your initials, are your more concentrated solutions. So 1.5 molar. How much of that? And MF is 0.25 molar. We want to make this final volume of 500 milliliters. So what will be the initial volume that I have to take of that 1.5 molar? 0.25 times 500 divided by 1.5, I get about 83.3 milliliters. Describe the steps you would perform to prepare the solution in A. Remember, take VI, 83.3 milliliters, of MI, 1.5 molar ammonium chloride, and dilute to VF, 500 milliliters, to get MF, 0.25 molar ammonium chloride. Okay, take VI of MI and dilute to VF to get MF. A stock solution is prepared by adding 312.8 grams of potassium chloride to 500 milliliters of water. How would you prepare 1 liter of 0.25 molar potassium chloride from this stock solution? You have two solutions. This last part, how would you prepare, is definitely an MIVI equals MFVF problem. There's two solutions here. There's two concentrations. We're just missing the first concentration. We're missing MI, right? Because we know what MF is. That's 0.25 molar. You know what VF is. That's 1 liter. We're just missing MI. We're going to use this information to get MI. So do that first. MI is going to be the moles of potassium chloride divided by the liters of solution. We know that we have 312.8 grams of potassium chloride. What's the molar mass of potassium chloride? 39.1 plus chlorine is 35.45, about 74.55. That's about 4.2 moles. So my MI is going to be 4.2 moles divided by 0.5 liters of solution. Just divide it by 1,000. 8.39 molar. There's my initial concentration. So 8.39 molar VI equals MF, 0.25 molar, times VF, 1 liter. What will be VI? 0.25 divided by 8.39, 0.03 about. Liters, I'm in liters, which is about 30 milliliters. So we will take 30 milliliters of the 8.39 molar KCl and dilute to what volume? 1 liter with water to get that final concentration of 0.25 molar potassium chloride. So there's my answer. Here's your big test. See if you can solve this. A 69.3 gram sample of oxalic acid was dissolved in 1 liter of solution. How would you prepare 1 liter of 0.15 molar oxalic acid from this solution? Do you recognize how to do this? Try it. The last part is definitely how would you prepare this solution. That's definitely an MIVI equals MFVF problem. We know VF is 1 liter. We know MF is 0.15 molar. Right? We just have to find MI. Mi is going to be the moles of oxalic acid all over the liters of solution. I have 69.3 grams of this oxalic acid. How many grams of this stuff are in a mole? So hydrogen 1.01 times 2 plus 12.01 times 2 plus 16 times 4, get about 90. About 0.77 moles. So my Mi is going to be 0.77 moles divided by 1 liter. 0.77 molar is Mi. Okay, now I have Mi VI equals MF VF. Let's get that VI. Mi is 0.77 molar. VI, MF is 0.15 molar. VF is 1 liter. Solve for VI. 0.15 times 1 divided by 0.77, 0.19 liters. All right, because my final units are in liters. So my answer, take 0.19 liters of 0.77 molar solution and dilute with water to 1 liter to get 0.15 molar oxalic acid. There's my answer. What is the volume in milliliters of 0.215 molar sulfuric acid containing 0.949 grams of sulfuric acid? This is not a dilution problem, straightforward molarity problem. They want to know volume, and that's going to be this part. Just have to solve for it. My molarity is 0.215 molar. My moles, I have to find it. I have 0.949 grams of sulfuric acid. Hydrogen is 1.01 times 2 plus sulfur, 32.1, plus 16 times 4, 98.12. You get about 9.7 times 10 to the negative 3 moles. 9.7 times 10 to the negative 3. All over the liters of solution. Move the liters of solution to the top. And the 0.215 molar to the bottom. Divided by 0.215, about 0.04. They want the answer in milliliters, though. So move the decimal place 3 places. 1, 2, 3. 40 milliliters. So in general, there's 2 types of problems that we need to be concerned with. One is a dilution problem. And the big hint there is that if you see 2 solutions, 2 concentrations, it's going to be a dilution problem. If you don't, it's a straightforward molarity problem, where molarity equals moles of solute over liters of solution.